Let's continue our study of control structures for arrays by looking at a program that will help you lie with statistics. Here's the problem statement. You've probably heard that there are lies, damn lies, in statistics, although the attribution of this quote is contested. In his wonderful book, How to Lie with Statistics, Darrell Huff demonstrates how to lie with statistics by using the ambiguity in the word average. So let's write a program that automates this process. First off, let's talk about what average means. What we're looking for is a single number that describes the middle of the data in some sense. So there are three candidate statistics. One is called the mean, and this is the sum of the values divided by the number of values. When most people think of an average, mean is actually what they think about. They're just not very precise in expressing themselves. But there are two other statistics that can be used too. There's the median, and what that is the middle value. So if you were to sort the values in order, the median would be the one that was right in the center. And then there's the mode, and that's the most common value. So that's another way of looking at a value that might be in the middle in some sense. So let's take a look at an example. Suppose our values are 1, 2, 2, 4, and 5. The mean is 1 plus 2 plus 2 plus 4 plus 5 divided by 5, because there are 5 values. Now that equals 2.8. Remember that I'm doing math here, not Java, so we're not seeing integer division. Now the median, on the other hand, is 2. If there are an even number of values, you take the mean of the center 2. The mode is also 2, because there are 2 2s and only one of each of the other values. If there's a tie, what you do is you take a mean of the tied values. Well, now, why do we have 3 averages? Well, for most people, the average is the mean, so what's going on with these other 2? There's a problem when one value is sort of out of whack. So, for example, if you find the mean of 1, 2, 3, 4, and 100,000, the mean is 20,002. So that 100,000 had a very disproportionate impact on the mean. And is that really what the middle of that data is, or is 3 closer to the mean? This gets to an important topic in statistics called robustness. It's very common to have automated equipment fail occasionally when you're capturing data. It's also common to have misunderstandings between different individuals who are collecting data. Sometimes they're purposeful, more often they're accidental, but either way, sometimes you get a data value or two that are just completely out of whack, and you need to fix that. So the nice thing about the median and the mode is they're less sensitive to these kinds of errors. So you get more reliable data, even though some of the data is a little bit strange. Here's how you lie with averages. You calculate the mean, the median, and the mode. Then you select the statistic that best suits your purpose. You label it generically as the average to avoid detection. So let's take a look at an example. Suppose in my last examination in this class that we had a mean of 83, a median of 85, and a mode of 46. If you wanted to argue for the grades to be scaled, some extra points added on, you might say that the average was only 46. On the other hand, if you're arguing that a project should be canceled because everybody already knows the material, then you'd say, well, but wait a minute, the average was 85. So this can be a very useful life skill. Politicians are experts at using this data. Of course, it's unethical to take advantage of the fact that people are somewhat innumerate sometimes. But on the other hand, if you're a politician or sometimes a student trying to get an advantage, what's a little bit of unethical behavior. So the first thing we need to do, as always, is to create some test data. So we want to start with a small file, and we definitely want to use int values. Now you might think, well, why aren't we using doubles? Well, the reason is, if you think about it, for things like the mode, we have to do equality comparisons. And remember, equality comparisons don't work very well with doubles. We also want to make sure we include some of the difficult cases. So even an odd number of elements, ties for the mode, things like that. A really good set of data to look at is 111, 222, 333, 444. So you have an even number of data elements, you've got ties all over the place, and better yet, the mean, the median, and the mode are all 2.5, so you know exactly what the answers should be. So that's kind of a clever test data set for us to use. So what we're going to do is put the number of values in the file first, and then enter the data themselves. That makes it easier because then we know how big to create our arrays. So here's the program structure. First, we're going to read the data from a file. Then we're going to calculate the mean. Then we're going to calculate the median. And then we're going to calculate the mode. We'll ask if the desired value is the largest or the smallest one, and then we'll return the desired value. The median algorithm, the easy way, is to sort the data and choose the middle. That sounds like fun. But what if we can't sort the data? Well, why wouldn't we be able to sort the data? I mean, we've learned sorting algorithms. Certainly that's a possibility. Well, the problem is sometimes the position of the data in the array already means something. And so then if you sort it, you mess that up. So for example, we might have the data sorted another way. Maybe we're doing binary search on the data another way. And so we can't just go around sorting everything just because we feel like it. There's a way to work around that, and that is to copy the data and then sort the copy. That doesn't damage the sorting order in the original array. But there's a problem. That doubles the memory usage. And so in some programs, that's not going to be acceptable when the arrays are large. Incidentally, the little tiny arrays we're working with in our examples wouldn't have this as a problem. But in general, sometimes sorting an array just isn't a possibility. So we're going to have to think through the details of another algorithm. This is a classic time-space trade-off problem, by the way, where we're having to exchange spending more time computing something to save a little bit of space in the memory. Sometimes those problems happen, sometimes they don't. Sometimes you can find solutions that are good for both time and space just by thinking a little bit more about your algorithm. Here's the idea. We're going to step through the values until we find one with the same number of elements that are smaller and larger. That value is the median. Now, this works for an odd number of data, but it isn't going to work for an even number of data. So for an even number of data, what we need to look at is to see if the number of smaller values plus 1 is equal to the number of larger. Or maybe, and, smaller is going to equal the number of larger values plus 1. So essentially what we need to do is count the number of smaller values, count the number of larger values, and then do a comparison. The problem case here is with ties. So what if we have the case like we do in our test data where we have ties right in the middle? Let's look at our test data. 111, 222, 333, 444. 1 has no smaller values and 9 larger values. 2 has 3 smaller values and 6 larger values. 3 has 6 smaller values and 3 larger values. And 4 has 9 smaller values and 0 larger values. So we have to find a way to make those numbers work. We need to consider how many values are actually equal to each other. So for example, 2 has 3 smaller and 6 larger, but it also has 3 equal values. 3 has 6 smaller and 3 larger, and it has 3 equal values. So now we can see how we can develop an algorithm that will make it possible to find the mode. We have to consider the smaller plus the equals equaling the larger, or the larger plus the equals equaling the smaller. Now I said equal, and we might want to think about whether that's the right comparison. So let's continue working on our algorithm for finding the median. We might think that the smaller plus equals has to be greater than or equal to larger, or maybe the larger plus equals has to be greater than or equal to smaller. But the problem here is that it doesn't handle the fact that we have to worry about how many values are in the array to make this work. What we need to have is that both sides of this are at least half. We have to consider when we think of half, should we be rounding up or rounding down? Math.round causes us problems here because what it does when you have a value that is right at 0.5 is that sometimes it rounds up and sometimes it rounds down. The details are in the Java API in the math class if you're interested in them. But we can't have that happening. We have to decide what should happen when we have half. We know that smaller plus equals is going to have to be greater than or equal to half, and larger plus equals is going to have to be greater than or equal to half. Now, should this be an and or should this be an or? Do we want one of these conditions to be true or do we want both of them to be true? Well, that's clearly going to have to be an and. So we've got a lot of little details to worry about when we're implementing this one, but at least now we have a concept. Let's stop for a minute before we go and jump into writing code and think about the process of what we've done here, because this is the process of developing algorithms, and it turns out this is one of the hardest things to learn how to do in computer science. It's a very complicated thing to learn. The first thing you need to do is to fully understand the known algorithms. So for example, the things that we're using in class are well-known algorithms that you sort of add to your toolkit and then you modify to use for particular examples. Abstraction can really help here. For example, do you realize that the mode calculation that we're doing in this problem is actually the exact same thing we did in the Texas infiltration problem? Well, it is. That's abstraction. Now, if you missed that, don't worry about it. Abstraction is one of those things that you have to practice and get better at. So let's take a look at our progression through this problem. We started with a challenging example. Then we considered a simple case first. That's where all the values were distinct. And then we considered the more challenging case. So we sort of worked up in degree of difficulty. We came up with ideas. We tested against our data until we eventually found something that's going to work. So now let's go and implement some code. Okay, so I've written a lot of this program for you because a lot of this program is pretty routine. I've also Java docked it, so I saved you a whole bunch of work there. Here's our main program. Now notice the main program had us reading data from the file. So let's go find our data file. So here's our data file. I called it testdata.txt. We have 12 values, so that's what the 12 is doing in there. And then we have 111, 222, 333, 444. Now we might want to think about whether that's really a good way to put our data in. Because it's sorted, we might be taking advantage of some magical properties. So that's something we might want to twist around later. So we're going to read from the file. The read from file method returns an array of data. Then we're going to find the statistics. So we have the double, that's the median, the mean, and the mode. And we have methods that returns each of those things. Then we ask the user if they'd like the highest or lowest value and read in their answer. If they say highest, we print out the largest one. Notice that I'm using the math.max method here in order to get the largest. And if they ask for the smallest, then we use the math.min method. Now I've written the find mean method for us because it's very similar to code we've already written. All you do is add up all the values in the array and then divide by the length. Do notice that I made the sum a double to start with? The reason I did that is so that when we did the division by the length, we wouldn't run into our integer division problem that we've encountered so many times. So here's our place for the find median program. So the first thing we want to do is to put in some comments to describe our algorithm. We're going to count the number of values that are smaller and larger than each value. And if we find one where the number of smaller values plus the number of equal values is greater than half, and the number of smaller values plus the number of equal values is greater than half. Whoops, and when I said smaller there, I meant larger values. Then we found one median. But remember, we have to worry about the fact that we may actually have two median values. We're going to add the median to a summation value and keep track of the number of medians. Then we'll average the medians found and return to the user. Okay, So now what we've done is basically taken all the thoughts we had when we were developing the algorithm and moved them into comments. This helps us keep the code organized, it helps us remember what the code is supposed to do, and makes programming a lot less painless. Now, if you're thinking that I have too many comments in there, not a chance. It's very unusual to have somebody that has too many comments in programming. Almost always they're going to be too few. Okay, so since we're counting the number of values that are smaller and larger than each value, we need to use a loop. So we'll start with I equals 0, I less than data.length, and increment I. So we have to figure out where this loop is going to end. So certainly counting the number of values for each number needs to be inside. The calculation of whether we found a median or not needs to be inside, and adding the median needs to be inside. But returning the median to the user does not need to be inside the loop. So that means now all of these lines need to be indented. So I highlight them and hit the tab. Okay, now to count the number of values that are smaller and larger, if you think about it, that means we need another loop. So here we're into a nested loop. I'm also going to make that a for loop. Now we need to be a little bit careful not to use the same counter. So I don't want to use I here, but I probably also don't want to use J. In fact, I'm really thinking hard about whether I was a good choice. The reason is that it's very easy to confuse I and J, and that's going to make our algorithm wrong. Remember, debugging is hard. It's much easier to write clean code. So let's change the number of that first variable and clean this up a little bit. So let's say that this is going to be our value. Much likely to get less confused with more meaningful names for data. And this one I'm going to call our test. Now again, we're creating a nested loop here, so we're going to indent one more time. Now let's think about where the end of that test is going to be. For example, when we find the number of smaller values and equal values, this part of the code right here, the part that's on lines 83 through 85, that doesn't need to be in this loop. So our inner for loop actually ends right there. The other steps will be done after the for loop is complete. If we're going to count the number of smaller and larger values and use them afterwards, we need to declare the variables before the loop. If we declare them inside the for loop, we won't have access to them after the loop. So we'll call smaller equals 0, larger equals 0, and equals equals 0. Notice that I cleverly called my variable equals instead of equal to avoid ambiguity. Equal, remember, is a method that we use a lot. If data of test is less than data of value. Well, if that's true, we want to increment the number of smallers. Else, if data of test equals data of value, then we want to increment the number that are equal, and else we increment the number that are larger. Notice we don't need to put an if statement there, because if something isn't smaller and something isn't equal, guess what? It's larger. So we now have the number of smaller, larger, and equal values. So we need to figure out how many values are going to be half. So let's create a variable called half, and now I've written int half equals data of length over 2, but we want to pause and really think about that. So if there are 10 values in the array, half would be 5, so that's going to work fine. But what if there are 11? Should half be 5 or should half be 6? If we leave it as it is right here, half would be 5. So we'd be looking for 5 values that are smaller or equal to, and 5 values that are bigger than or equal to. So that sounds like it's going to work. So now it's time to put in the actual work of this code. So if smaller plus equals is greater than or equal to half, and larger plus equals is greater than or equal to half, at that point we have a candidate for our median. Now we're going to need to think about where that median needs to be. If we declare it here, it only will live between those curly braces, so that isn't going to work. If we declare it here, for example, like we did with half, then it will only live within our first for loop. But we need to return this at the end, and that happens after the for loop. So we're going to have to go above the for loop to declare the variables. So here we go. There's our inner for loop. Here's our outer for loop. And I'm going to create an int called medium sum and set it to 0. And I'm going to create an int called medium count and set it to 0. Now we might want to do a little bit of thinking about whether an int is such a good idea here. At the end, we know we're going to be dividing median sum by median count. Well, those are two integers. If we divide them, we get an integer, and that's going to truncate. Don't want to do that. So let's just make this a double right now and initialize it to 0.0. Okay, so if those are true, then we have median sum plus equals data of value. And median count equals median count plus 1. But remember, we have a neat little shorthand for that now. I see what Eclipse is unhappy about. I misspelled our variable name. And I guess I decided to add in an extra semicolon there too. Okay, so this is when we find a value that's going to be the median. And now, outside of the for loop, we're going to return median sum divided by median count. Now, we haven't implemented our method for mode yet, but we could test our median method. And remember, we always want to test as often and as soon as we can. So let's run the program. So the name of the file that contains the data is testdata.txt. Do we want the highest or the lowest value? Well, let's say the highest for now. The largest average is 2.5. We actually don't know that our median program is running correctly right now because we've hidden it. So what we need to do is to put in some testing output. So let's go back to our main program and make an adjustment. Although it is kind of encouraging that the value we were expecting did come out. So here's where we were printing before. There's our three values being calculated, our mean, our median, and our mode. So let's just put in some debugging output right here. The mean is plus mean, system out print line. The median is plus median, system out print line. The mode is plus mode. So that way we'll be able to look at all three parts. And in fact, I'm actually going to do something else here. I'm going to terminate the program at this point. Now, I'm not taking out the code that's here. Ah, yes, Eclipse is unhappy about that. And it's actually not going to be unhappy even if I fix what it's unhappy about. So what it's unhappy about is system exit actually takes an integer parameter. Now, a parameter of 0 means everything's okay, and a parameter of 1 means there's a problem. So this will fix it, and that's a way to stop the program. But notice we then have unreachable code. I'm a little surprised that Eclipse isn't detecting this, but since it isn't, hey, what the heck, let's go ahead. So now we can run and actually get an idea of whether our program is working correctly. So this is test data.text, and the mean and median are both correct. So now we know we've got our program right. So that's good. Well, when I say we know we have our program right, that's always a hard thing to determine. Remember, for example, that we had our data in sorted order. We don't think that made any difference, but then again, it might have. So you always have to consider those things. In other words, we haven't tested our program enough to really know whether it's right or wrong, but the early results are encouraging. So let's now think about the algorithm for the mode. We need to keep track of how many times the most common value has occurred. So for each value in the array, we're going to have to find the number of times that value occurred. Notice that we're relying on these values being integers so that we can make equality comparisons meaningfully. Then we've got two different cases to consider. If the number of times this value occurred is equal to the maximum number of times that some other value has occurred, then we need to add to the running sum of the modal values and increment the number of modes that have been found. If this number is greater than the maximum, we need to reset the running sum and reset the number of maximum values that have occurred to 1. So there's our algorithm. Once again, when we were doing the problem previously with our Texas infiltration, we had sorted the data, and so we were able to use some of the special properties in the sorting. Without those properties, then we need to be a little bit more clever. So let's talk about the design of the method signatures. When we're reading the data from the file, we need to have the file name as an input, and we'll get our array of data back as a return value. Now that method I've already implemented for you, as you saw. FindMean takes an integer array of data, the array that was read in by read data from file, and it returns a double that represents the mean. That method I also implemented for you. Now FindMedian and FindMode are also similar in that they take the array of data and return a double. Notice that I've kept the names of the methods and everything completely parallel. Everything's in the same order. By doing that, it makes it much easier to use the code. Here's our method for finding the mode. So we need to find the number of times each value occurred in the array. If our count is larger than the previous maximum, we need to replace the previous maximum. If our count is equal to the previous maximum, we need to increment our previous maximum. Well, so that gives us some ideas for what some of our variables should be. We're going to have a double, which I'll call mode sum, and an int I'll call mode count. Of course, both of these variables need to be initialized to 0. So we're going to need to have a for loop here because we're going to need to step through every element in the array. And notice that I have fallen back once again into my bad habit of using I as a counter too many times. Let's fix that. Let's just do it right the first time here. We need to think about what's going to be inside this outer for loop. So these computations, like our count being larger than the previous maximum or equal, those need to be inside the outer for loop. So all those should be indented. And that's where our for loop should end. Now remember, we're going to have to do some computations afterwards. In particular, we're going to return our mode sum divided by our mode count. Okay, so those things are all set. Now let's return to our loop. We need to find the number of times that each value occurred in the array. Well, if you think about it, that's another loop. So once again, a nested for loop. So this is our standard counting nested for loop. Int count equals 0, count less than data.length, plus plus count. Now we need to think about where this loop is going to end. Our computation, if the count is larger than the previous maximum, has to occur after we've finished our count. So that means that our for loop should end here. Now I'm going to put a comment in there so we know exactly which for loop is ending and what we meant that parenthesis to do. So if data of value equals data of count, then we increment our count. Now we haven't actually created a variable for that, so we had better do that. So I'll call it count values is 0. So this is count values that gets incremented here. We might stop and think for just a minute whether it's okay to use equals equals there. Remember, data of value is an integer and data of int is an integer. And it is okay to use equals equals with integer. We use dot equals, remember, with object types. Okay, so now we're ready to do our comparisons inside the first for loop and outside of the second one. So if count values is greater than or equal, oh, we said larger, so remember that's just greater than. So if we found a value that's occurred more times than any value we've seen before, then what we do is we say mode count equals count values, and our mode sum equals data of, which data should we be using here? Let's think about that for a minute. Have we kept track of it? Well, we're inside a loop with data of value, so that's the one we want. Okay, here's our second case now. And remember, we had a comment for that case, so let's go down below it so that we can see our nice comment. Our comment says if count is equal to the previous maximum, we need to increment the previous maximum. So this will be else if count values equals mode count. So that's the equality case. Then mode count gets incremented. So that's plus plus mode count. And mode sum equals mode sum plus data of value. Okay, and then at the end we return mode sum divided by mode count. So it looks like our method is done. So let's run a test and see how things are looking. So here's our test, data.text. Okay, so we have an unexpected result. Now we need to debug the program. So the first thing you do when you debug is you go back and you read carefully, because that's how you find most of your mistakes. This is actually a research result. People have studied this and found that that's the best way to debug things. So remember to do that first. So let's go back and reread the code. We have our mode sum and our mode count, both of which we remembered to initialize, so that's good. We step through the values one at a time. Then we initialized the count of the value to 0 and found the number of times that occurred. We did that in a nested for loop, and that code looks really good, very unlikely to be the source of the error. Let's take a look at what happened down here. Because this is logically more complicated code, it's much more likely to be the source of the problem. So we started with count values and we compared it to mode count. So then we reset mode count to count values and reset the mode sum to data values. It looks like there's something wrong here because we're not keeping track of the maximum number of times the value occurred. Since we don't know that, we really don't know which case we're in. In other words, we forgot to declare a variable that we need. So let's go back and declare it and fix this code a little bit. So we'll have an int for the maximum mode count, and we're going to initialize that to 0, 2. Now the mode sum will keep track of the maximum every time it occurs. The mode count will keep track of the number of times it's occurred, and the maximum mode count will keep track of where we are so we know that if a new one is better than our existing one. So we needed 3 pieces, not 2. Pretty typical programming mistake. So now let's think through our logic very carefully. If the count value is higher than the maximum mode count, that's what we were missing last time, then we set the mode count to 1 because this mode has occurred just once. We set the mode sum to data value, and we set the maximum mode count to count values. So now we have all 3 pieces of the puzzle taken care of. Now, when they're, forgot an S in count values. Now, when the 2 are equal, we want to increment the mode count and increment the mode sum. We don't want to reset the maximum mode count there because at this point the maximum mode count is the same. We basically have found another tie. So this looks much better now. So let's just finish reading our code. Remember, mode sum was a double and mode count was an integer. We know that wasn't the problem because the mode we were calculating was 0.5. So it looks like we've probably found the problem. Let's run the code and see. Entering the test data file. Well, that was disappointing. We didn't fix the problem. So it's time to go back and carefully read the code again. So if the count values was greater than the maximum mode count, then we reset the mode count to 1, we added the value to the mode sum, and set the maximum mode count to count values. And now we see the problem in our next test. I remembered to change the top one to maximum mode count, but I forgot to change the next one. And so we were looking at the wrong value again. That looks better. So let's run our program again and see if things are working better. So here's the name of our file. And there we go. Well, thank goodness. That certainly was a struggle. Keep programming.